This is the third mini lecture for section 7.1, the textbook. So a decimal like 0.3333, where the 3's keep repeating, it's called a repeating decimal. We can write it as 0.3 with a bar over the 3. That bar just means that the digit keeps repeating. Any decimal that has a single digit or a string of digits that just keeps repeating from some point on is called a repeating decimal. Sorry, someone's Facebook messaging me. So, for example, 0.432323232 is 0.432 with the bar over the 32, and so on and so forth. So these are all what we call repeating decimals. So it turns out that every repeating decimal can be written as a fraction, using the same idea that we used for 1/3. Let's do a few examples. Let's try. Let's try. Let's consider the number x equals 0.414141 and so on, or 0.41 with the bar over the 41. Okay, I just made that up off the top of my head. Okay, the idea is to take powers of 10 times this x so that when we subtract, the decimal part cancels out. And here, what I'm going to use is 100 times x, which is 41.4141, dot dot dot. And then x itself is 0.4141 dot dot dot. And you can see now the reason why I did 100x, because the 4's line up with the 4's and the 1's line up with the 1's, and when I subtract, on this side I'm going to get 99x. On the other side I'd get just 41, because the 4's and the 1's past the decimal point I'll cancel out. So x is 41 over 99. And I can test that on my calculator and make sure quite easily. So if I do 41 divided by 99, then there's that infinite decimal expansion. Okay, let's try a couple more examples of that. Let's say, consider x equals 3.177777 and so on, or 3.17 with the bar over the 7. So it just keeps going on and on forever. So again, what I want to do is try to eliminate the repeating tail of this number. Here, the repetition doesn't start right after the decimal point. It starts 2 places after that. So I'm going to begin with 100 times x, which would be 317.7777 dot dot dot. And then if I do 10 times x, that is 31.7777 dot dot dot. And the reason I did those 2 powers of 10 is I knew that they would both have that repeating tail of 7's past the decimal point. And that's all that they have, past the decimal point. So when I subtract, on this side I get 90 times x, because 100 minus 10 is 90. On this side it's 317 minus 31. Okay, I get 286. And all that decimal stuff cancels out. So that means that x is 286 over 90. And why don't we simplify that? would be 143 over 45. And that's as far as we could take that. So there's the fraction, or the rational number that's represented by that decimal expansion. And again, I can check this easily by just doing 143 divided by 45, and there it is. You know, there's a little bit of a rounding error. Okay, and this process I'm doing here, actually, it actually is not something you could ever do on a calculator. You will always be a little bit off if you try to use a calculator for this. You can only use pencil and paper. But you can use a calculator to check your work very easily. Let me try just one more. Let's consider x equals 0.123, 123, and so on. So here I would use 1,000 times x to start off with. So give me 123.123, 123, dot, dot, dot. And then x is 0.123, 123, dot, dot, dot. And now if I take the difference, I have 999x equals 123, because the decimal stuff cancels out. So therefore x is 123 over 999. And those are both divisible by 3. So let's see, we get 41 over 333. And again, you know, you can check that. You know, I'll do it with lots of decimal places. So 41 divided by 333 is that. So it just keeps going and going. Okay, so we're getting closer to our final answer about decimals and fractions. We are seeing that every repeating decimal represents a fraction. And every fraction apparently represents either a terminating or a repeating decimal. Okay, we still kind of need to test that last part. We can use long division. This is long division with decimals, which you might need to review in section 7.2. We can use long division to write any fraction as a terminating or a repeating decimal. So for example, you know, a couple slides ago, we did 13 over 40. Let's try that again. But let's use long division. So I'm dividing 40 into 13, and I just tack on some zeros there in case I need them. See, 4 doesn't go into 13, so we'll try 40 doesn't go into 13, so we'll do 40 into 130. It goes in there 3 times. Minus 120, subtract, get 10, drop to 0. 40 goes into 100 twice. Subtract, we get 20, drop to 0. 40 goes into 200 5 times even. So we get 0 and then we're done. So this tells me that 13 over 40 is 0.325. So there's a second method for doing that. Now this also works for fractions that would give you repeating decimals. For example, let's try 5 over 11. So if I divide 11 into 5, see 11 goes into 50 4 times. Get 6 left over, drop to 0. 11 goes into 65 times. Subtract, I get 5, drop to 0. 11 goes into 54 times. Subtract, get 6. 11 goes into 65 times. And you see, this is just going to keep repeating. We're going to keep getting 4, 5, 4, 5, and so on. This pattern, like we see right here, that's just going to repeat forever, because I just have zeros from here on out. Nothing's going to change to alter this pattern. So I can see that's going to keep going. So therefore, 5 elevenths is 0.45 repeating. So this means that we are now ready to finally answer the question that we started this discussion with. Every rational number has a decimal expansion that is either terminating or repeating. Every terminating or repeating decimal expansion represents a rational number. Okay, a number that is represented by a decimal expansion that is not terminating and not repeating is called an irrational number. So the word irrational just means not rational. But in terms of the decimal expansion, it means that its decimal expansion is not terminating and not repeating. So if you ask, well, what decimal expansions represent fractions or rational numbers? Well, it's the expansions that either terminate, that means they cut off after some point, or they repeat forever after some point. And if it doesn't terminate and doesn't repeat, then it's what you call an irrational number. Okay, a good example of an irrational number is the square root of 2. So if you do the square root of 2 on a calculator, 2, hit the square root button, and you see that it's just this jumble of digits. There's no pattern to it. It doesn't repeat after any point. 4, 1, 4, 2, 1, 3, 5, 2, 6, 3, 7, 3, 0, 9, 5, blah, 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 forever. So the square root of 2 is an example of a number that's not rational. Another good example is the number pi. Okay, the ratio of the circumference of a circle to its diameter. That just goes on forever without any repetition. It doesn't start repeating after some point. Sections of it repeat here and there, but it doesn't just start cycling after any point. So make sure you know some good examples of irrational numbers. Those are numbers that can't be written as fractions, because I often see them come up on certification exams. So the real numbers, taken all together, consist of all the rational and all the irrational numbers. So if we just basically take all the decimal expansions, the repeating ones, the terminating ones, the non-repeating ones, those all together make up what we call the real numbers. And the real numbers are the number line. So when we add in all those other decimal expansions, we've completely filled in the number line. So the real numbers are in a one-to-one correspondence with the points on the number line. So this kind of concludes our development of the number line. It's finished now.